And with that, it's my pleasure to introduce our own Hao Su as the next speaker of the session. Professor Hao Su from City University of New York, right here in New York. He's the Erwin Zahn Assistant Professor there. Did his doctoral work at Worcester, and then postdoc at Harvard and WIS, and well known for work on mechanism design, ranging from surgical robots to socially assistive robots, numerous applications. And with that, Hao, please take it away.
Okay. Sorry. I hope everyone is staying safe and healthy during this challenging moment. Today, I would like to share with you our work that is at the intersection of design and control of software robots. Our lab focuses on high-performance software robots. As Professor Sudhumuri said, we are trying to do high forces and all high-speed software robots, and with applications in surgery and rehabilitation. This is a truly fascinating and emerging field that involves many fundamental research and exciting applications to solve real-world problems. And we believe that a software robot could be translational medicine to improve quality of life in our society. In my lab, we focus on two domains. And on the left, one domain is robotics, and where we study design and control. And our approach is unique because we create enabling technologies like sensors and actuators. We also design robots from scratch. Then we develop controllers to embody intelligence to robots. On the right side, the other domain is scientific discovery. The ultimate goal is translational medicine. We use robots to address the unmet needs in medicine. Then we leverage robots to understand medicine and biology. My lab developed multiple high-performance software robot platforms in the continuum care, ranging from soft exoskeleton for musculoskeletal injury prevention to cancer diagnosis and treatment using custom MRI-compatible minimally invasive surgical robots. In the last 3 years, we also work on exoskeleton, both rigid one and also soft ones. The goal is to enable community-based mobility assistance. However, if we observe robots, wearable robots, through the lens of design and control, in terms of compliance and lightweight, state-of-the-art exoskeletons have no difference with conventional industrial robots that are generally heavy, rigid, non-compliant, and even dangerous. In terms of intelligence, researchers developed a tethered exoskeleton that can assist running. But this platform you see here, right, is still kind of like a heavy tether, right? And to improve compliance, researchers developed like an exosuit approach, which is really very promising solution. The overall mass is around like 5.5 kilograms. It's still a little bit heavy, right? Even for able-bodied population. My lab, we think we developed the most lightweight powered exoskeleton. So that's our focus. And to enable robots truly useful in real world, we need design solutions to make robots as light as possible. On the other hand, we also need new controllers to make the robot really versatile for multiple locomotion activities. So I would like to share two lessons I learned in the last few years. The first one is first principle-based thinking for design and mechanism. First principle, as Elon Musk said, right, is a physics way to look at world. So you boil things down to the most fundamental truth, then you reason up from there, right? So for wearable robot application, we consider actuator or the motor has a lot of space to utilize the first principle to make it better. Similar to sand-based idea, we are also trying to promote this quasi-direct drive actuation. So as you can see, for the conventional actuators, using high gear ratio transmission is good in terms of bandwidth, but pretty mediocre in terms of compliance and efficiency. Series elastic actuator has some benefits by using a spring to improve the compliance, but the bandwidth and efficiency is still not very good, right? So similar to sand-based approach, we are doing a lot of quasi-direct drive actuation, but our major focus is to potentially design better motors than commercially available actuators. So the custom motor with high torque density can truly optimize all three metrics. Our electric motor, for example, is not only have high power density, but also have a really high torque density, roughly close to 10 times better than a Maxar motor, and basically about 10% mass of conventional motors if you normalize by this so-called torque density, and also about twice better than this T motor used in many quasi-direct drive actuation platforms. To achieve those performance, we develop physics-informed design methods. For example, one method is called topology optimization. Instead of a conventional motors that is based on interior rotor design, we create exterior rotor topology. And you can see from this bottom right figure, and exterior rotor can significantly increase a torque density. So we also did a material optimization, some other physics-informed design methods. Another observation from about first principle based thinking is to figure out what is an actuator. Right? This sounds like a silly question, but if you really think about conventional rigid robot, but it's kind of compliant, right? Like SEA or our own rigid but a compliant robot, it's difficult to align a human joint with a robot joint, right? So our approach is trying to borrow from a software robot community, avoid this joint misalignment issue. But if we really think about actuator, and in software robots community, we typically talk about pneumatics and actuator, right? But if you really look at the transmission and actuator diagram, actually the tethered palm, it is a true actuator, because the true actuator is a component that converts electrical energy to mechanical energy, right? So the pneumatics, I think, is actually transmission, not the true actuator, right? So how can we tackle the grand challenges in software robots that are typically slow, weak, and tethered, and to make this to design untethered and high force software robots? So in my lab, we have two approaches. The first one is we leverage the motor technology. It's still the rigid motor, but we use it in concert with hydraulic artificial muscle. The second concept is we focus on this transmission design and use the best stable pneumatics to make the robot have high performance. For example, our first approach, this is a motor-based approach for hydraulic artificial muscle, is truly durable, can generate high forces, and the overall mass is within 2.5 kilograms, including battery. So that's truly an untethered high force, a soft actuator that can potentially used for human augmentation applications. As you can see, it's very resilient. And also we explored this instability-based soft actuator, right? Besides the motor innovation, we focus on this transmission innovation. This is the first instability-based high-performance software robot. the robot has two stable states and one unstable state. So it can switch between those like stable states and leverage this nonlinear phenomena to rapidly switch. And it's 20 times faster than conventional soft actuator. The second lesson we want to share is kind of like a use-inspired design. So we want the robot to be practical, but also quest for basic understanding. We don't want to be in the third quadrant, and we want to be in the first quadrant, right? So we work a lot with doctors and from leading hospitals, and also we have physical therapists and biomechanics in my lab on residency. But if you only talk with your customers, right? Like Henry Ford said, if he talked with the customers what they wanted, they would tell you they want a faster house, right? People don't know what they want until you show it to them, right? So that's the key challenge, right? So in my lab, we try to come up with the best design solution. And we think this is the most lightweight powered exoskeleton for lower limb assistance. It has a significantly higher torque density and can potentially reduce about 25% metabolic cost. And we also do a lot of control work and to estimate a human joint movement in real time. And just play a short video.
The design, it actually helped me. I felt that I had more stability, it helped my balance, and my gait kind of went very natural. I felt very comfortable in the sense of, wow, this is going to be my friend.
I love it. It took about, a minute because it's pretty easy. I'm walking a lot lighter. It's very low profile. I don't hear noise when I'm walking. Everyday use, this is perfect.
They have to tell us what they need. They have to tell us what they want so that when we finalize the soft exoskeleton, it is something that will be useful, meaningful, something that will help them in their recovery and their activities of daily living.
We also applied this exoskeleton for a different population, for people with knee osteoarthritis. We can reduce their pain about 80%. We envisioned the robot could be medicine for people with musculoskeletal disorders. And we are also developing versatile controller for multiple activity augmentation. This is really a grand challenge in wearable robot community. Our controller can switch smoothly from loaded walking, jumping, and squatting without using activity classifier. So more importantly, we observe really promising results. We can augment human for loaded walking. People can jump higher and also squat about 50% more. Lastly, I want to share one quote from Da Vinci. Simplicity is the ultimate sophistication. So try to keep your design simple. Thank you.
Okay, thank you, Hao. A round of applause for Hao and for all the speakers of our first session this morning. If you have any questions for Hao, please type them into the Q&A and he will take them there.